I'm Dave Landsman. I'm from Western Digital, and Daniel Hadash here is with me from Twist Bioscience, and we're representing the DNA Data Storage Alliance. So we're going to talk a little bit about DNA data storage today. Why are we here talking about this? There's a general problem of too much data, right? We're seeing increasing scalability. Increasing density is scaling, and because people want to digitize everything, and magnetic storage is kind of slowing down. So tapes and HDDs, I'm not going to go into the chart, but this chart shows kind of the trends that areal density is slowing down, and if you want to get to bit size and track pitch and just the density that you need to do zettascale storage, something like DNA can get you down into the 1 by 1 nanometer range, and magnetic media is just not going to get there. So we need an adjunct to new storage. The supply also can't keep up with the demand, right? We're digitizing everything at great rates, and nobody wants to throw it away, and it's getting more and more expensive to keep it. So this gap between what we want to save and what we can afford to save is changing, or it's getting unmanageable. And so this is creating demand for new media types, potentially like molecular storage or glass or silica, other novel types of storage that can be very high density, very low power, etc. So, and the other thing that's becoming a real problem when you talk about archival storage at great scale is the fixity checks and refresh, right? It's becoming, people are getting to the point where if they have a huge tape library, they're by the time they're done, filling it up and storing it, they have to start refreshing it, and then then by the time they're done refreshing it, that they have to refresh it again. So, and then of course, last but not least, there's sustainability considerations. I mean, the hyperscalers are having trouble building these huge, paying for the power and the environmental impact of gigantic data centers. So this is driving the need for DNA data storage.
What does the track pitch mean in DNA?
Actually, that's a great question. Track pitch, it doesn't really mean anything, right? DNA is a volumetric medium, and so really, when you're talking about DNA, you're talking about a molecule. It's roughly a nanometer by a nanometer cube, and it's floating around in a pool. But for the purposes of comparing the traditional media, we had to use.
It's just a way to visualize like where DNA sits next to other storage media by how people see and currently measure the storage mediums.
We won't be doing block storage and tracks and on DNA.
Thought maybe you're going to embed it in a cube or something like that.
Well, which is great segue to this slide. So why DNA? So it is really small, okay, and just to give you an idea. Everybody has their own thing, like we can fit the entire internet in a shoebox, et cetera. But this kind of makes a little more sense to me, which is that if you took DNA bits and you filled the volume of an LTO9 tape, just filled the case up, right? That volume you would hold like 2 exabytes of data, or over 115,000 tapes worth. So it's just the density of DNA the scale is incredible. It's a quantum leap from existing storage. Also, it can last a really long time. We've seen, people have heard the stories of recovering DNA from fossil remains, and you can imagine that in a data center environment where we're doing controlled storage, it'll be even easier to maintain DNA-based data for a very long time. And other things are really important about it is the TCO is quite compelling because you don't need migrations like we were discussing. There's essentially almost zero cost for data at rest in terms of power and things like that. The essential technology of DNA is that you make a lot of copies of the molecules due to the processes used. So it's easy to make copies of databases, and they're small, so they're easy to store. Because of these, they're also very sustainable, right? Because of those qualities, and there is kind of an issue with synthesis today. Phosphoramidite chemistry synthesis uses some caustic chemicals, but there are new techniques which Daniel will talk. Well, Daniel will get into synthesis a little bit, but enzymatic synthesis is coming on stream, and that uses aqueous-based solutions and is really very environmentally friendly. The other thing about DNA is it's format immutable. And for those of you who remember like buying zip drives and you have a drive for a while, then you can't read the data on it and there's no readers. The molecule of DNA will always be able to be read. I mean, the reading and writing technology may change around it, but the fundamental molecular format will always be able to be read. So this is a very important quality of DNA. And we'll always be able to build. And everybody isn't, the world is investing and will continue to invest in DNA technologies because of biotech and medical applications and hopefully data storage.
So you haven't addressed the real issue, which is you don't have a high enough bandwidth interface to be able to use that much density.
Yes, we'll talk about it. The real, not yet. And there will be big challenges mainly through parallelization on chip to get enough bandwidth to handle certain applications. Like early applications will probably be archival kinds of applications where read and write speeds aren't critical or as critical. And we're not trying to make DNA be it's not replacing existing media. It's a new kind of media. Now,
I understand, but at the same time, how long will it take you to write 2 exabytes of data?
Or even one.
Or even one, yes.
Yeah, so you would be able, so the idea is that you can do things like very efficiently in parallel in DNA. It will take you a day to write huge amounts of data. It can be tens of petabytes or hundreds of petabytes. That's where we're aiming to get to. In order to support the loads, because we are aware of the loads that will come and the loads that are needed in order to support archival storage today.
Okay,
so it's not hidden from us, and it's not something we ignore and say kind of like this is not an issue.
Far faster than I would have expected, but okay.
So right, conceptually, you guys may already know, or the audience may already know, the concept of storing data in DNA is fairly straightforward. The information in DNA is already a code. We have these basic building blocks of 4 bases, and that encodes genetic information, and that's given to us by nature. What has changed really kind of fundamentally is that we can now build molecules of DNA, right, due to all the biotech, mainly medical applications, but we can now build molecules of DNA base by base. So this, very simply, the devil is in the details in terms of bandwidth and all these other things, but we can encode bits and files and digital objects into DNA molecules and bring them back out again. So that's kind of just the fundamentals of the pipeline. Now, I came from the tech industry. I'm not a biologist or a chemist. I'm more of an engineering computer science guy. But as I was learning about all this, it jumped out at me that many aspects of what we do with DNA are kind of like what we understand about a traditional network channel or an electrical channel, right? And we're used to the layered architecture of a network channel where we packetize data, we route things across switches, we control flow. At the physical level, we do bit scrambling for analog effects on lines. And so there's this whole layered protocol that we put into fields of electronic data. And there's kind of a similar abstraction that applies to DNA. So if we have a bit on the lower side, if we put a bit stream coming in, we're going to a file is going to have to be broken down into very small pieces of DNA, say 150 to 200 bases, and that may hold 20, 30 bytes. So we're going to do a lot of packetizing, right? So we have to packetize data. We have to put addresses in the packets. We do have to insert when we convert from ones and zeros into first we convert from ones and zeros to encoded fields, and then we convert to bases. And along the way, we do ECC insertion so that we can, when we get to the other side, we can decode and the sequence, after we've sequenced, we can then decode. So the whole, so anyway, the transport layer of DNA has very similar functions in concept to what goes on in electrical channel, although they're all done in the software codecs. Okay, so that's my last slide. I'm going to let Daniel talk about the phi, mainly, and whatever else we
What
get
about
into.
packet loss, stuff like that during the transfer? You're going to have replicated versions of the packets as well as the whole data set, let's say?
That's
We'll have enough left due to replication, and you can recover from a number of
Problem.
many errors, substitutions, deletions. You can recover from many of those, and I'll let Daniel speak to that more. So.
Yeah, so to that question, we need to think about it. It's a different technology. It's a different way on how it works. When we do the synthesis, this is the process of writing. It's not like I produce one packet for each packet of data that I need to. When I do the synthesis, I use chemicals and I put it on this 2D microchip that you see on the right side. And when I put the chemicals, it creates thousands or tens of thousands of copies of each packet. So in case you have some errors in one of those copies or few of them, or a replacement of a letter because of errors, you still have a lot of good copies in it. And what a sequencer does, and I'll get to it, is able to read a lot of them and find a consensus sequence of all of them to say, okay, this seems like the right packet. And this is in addition into the ECCs that we are inserting inside the packet after you read it.
So you're basically putting erasure coding into the system.
Yeah, and it's a very interesting challenge for the community because it introduced new ways of errors that were not in other channels before. So it's an interesting problem to solve. And so I'll do a bit of a deep dive into the physical layer, into the three main pillars of DNA storage, which is the synthesis, the storage, and the sequencing. Synthesis is the writing, storage is storage, and the sequencing is the reading part of it.
Is sequencing destructive?
Yes and no. So there are the technologies today are, but there are ways and groups that are working on non-destructive reading. But the ability that we have free copies, almost free copies, the ability to make a lot of copies, it allows us to kind of either create before a lot of copies, or once we want to read, create another copy and be able to preserve.
We now have WARO data, write once, read once.
So the DNA exists in these cells in this chip. Is that how this works, or?
So yeah, basically this array is you see here very a zoomed-in view of a CMOS chip that basically those are electrochemical reactors that we can control each one of them. And the DNA grows inside each one of them, and you build letter after letter in each one of them until you get to a length of 150 or 200 letters.
Each
in
of
most
those
cases.
cells would have 150 to 200.
You can think of it as growing small weed or kind of trees inside, so strands of DNA grow in each one of them. And in each one, it's the same packet, it's the same strand.
In each well. And
That's
this
your multiplication in your data copies at the very basis.
Yeah.
Making thousands and thousands of copies
exactly.
to put into the system. Okay.
and just to give you a little idea of scale, this particular paper, the chip that this study that they built this chip for, this chip can synthesize had about 32 million synthesis sites per centimeter squared. Commercially, we need to scale a lot more than that, and that's going to be a challenge. But this is how we're going to scale.
But this really takes the semiconductor industry to its limits and stuff. We go to the fabs and stuff, and this is a very a complex.
It's be considered like a read-write head for normal structural disk or something like that. So you're inputting bits, and out of these come out the DNA code that has all the information. Are you piping the DNA to some other storage medium then at this point?
Yeah. So basically, after synthesis, the DNA is washed into a tube. Then we amplify it and create even more copies. We purify it, and then we package it. And I'll talk on the next slide on the packaging. It's important to know that kind of the chip capacity is kind of like a very important factor in scaling it. And this is limited by the array pitch and the chip size. We cannot just make a chip on the size of a table. And right now, as far as it looks, we need to also make enough DNA in each of those small sites in order to practically store it. So it looks like 1 terabyte from a chip is kind of the practical limit, but we're able to make a lot of chips in one system. And this is to your question about the bandwidth, that we can make like hundreds or more of terabytes in every run of the system. And then you can multiply the writers, and then you can get to the petabyte.
My question now becomes, you say it gets washed into a tube. How do you maintain sequence? How do you maintain ordering?
They're
Exactly.
all tagged
So
with the address.
this is one of the problems that we tackle in the DNA Storage Alliance in one of the groups, is to develop a spec and a standard on how to find data in that huge pool of sequences, as we don't have physical arrangement. We cannot just go to the first sector of a drive or a tape. And we can dive into it a bit later, but there is a way to identify specific sequences or file, and I have a slide on it about like the random access.
Are the chips consuming like base chemicals and stuff like that? Is this the consumable chip? I mean, or is it you feed it more information and more base pairs and information, and it can continue to synthesize?
Yeah, so the chip is reusable, if that was the question, and we can wash it and run it again. I cannot just like put as much chemicals as I want because of the size of the wells in it. There is so much it can absorb. But we make enough DNA like in order to make a lot of copies over there.
I guess the question is, where is the base pair? Where's the base chemicals coming from in this sort of chip? Are they embedded in the chip itself, or is it something you can feed into it?
So it's a system that has like you have like bottles, like so today it's kind of an inkjet printer, kind of like you have a bottle of A, G, T, and C.
Right.
And then you can pipe it, and if you put it in a data center, you can have it in a different room and pipe it through to all the machines.
And so the chip has effectively 4 pipes coming into each of these synthesizer things, and it does the synthesis.
It goes into the printer head that goes above the chip and puts like and wash it with the chemical, and then wash it with another one to clean it, and then another one.
At a very small scale.
Yeah.
For the record, this is way crazier than I had imagined. The 1 terabyte chip that you talked about, how big is this chip?
Like it's around that size. Yeah. We're still not there. Like we're working on it. This is like so IARPA put like a roadmap for it and funded it, and we are like in the gigabyte scale these days. But again, you can see the IARPA goals is to get to 1 petabyte per chip or $1 per terabyte achieved by 2030. I'm not sure if it will be 1 petabyte per chip or per system, probably per system. But we're aiming to that price range in general, the industry. And as Dave said, a very important one is the enzymatic DNA synthesis, because we want to have it water-based, it's more environmentally friendly, more sustainable, and eventually it might be cheaper, and you can also make longer sequences with it. So when we talked about the 150 or 200, if we make it longer, we can improve the cost. So the next pillar is the storage. So basically the worst enemy of DNA is oxygen and water. And basically if we're able to hermetically seal the DNA, then we can get to a very long shelf life. And what you see here, that was a research that was done. You can have the source here. And you can see that if we hermetically seal it, we get to like 38,000 years at room temperature, which is quite amazing to any other storage technology. Yeah, but as we showed, the DNA is super dense. We also need to make it practical. So we cannot just store a zettabyte in like one capsule like that. It will be very hard to manage. You don't want to move a zettabyte here and there. You want to be able to split it and have machines or robots to move it around and take it between the different system, between different sequencers and readers and inside the data center. So basically we can split it and we can make an array of those containers, and then we can have an array sizes of like 100 terabyte or like a 96, 384, 1536. And then the sequencing. So the sequencing is the reading part of DNA. There are two main technologies these days. You can see it on the right of how to read DNA. And the thing is that sequencers were mainly focused on bio applications because this is what they were developed for, to read human DNA and to be able to analyze that. And currently it's practical up to a gigabyte class of DNA data storage. And we would need new innovation over there, and some groups are working on it to develop like a higher capacity sequencers and faster ones. Currently, a single run of a sequencer goes between 12 hours to 36 or 48 hours. And the cost is declining. We see it already because of the demand for how much of the sequencing that we need for us. Like we want to sequence more humans, more animals, more plants, and learn about us and the nature around us. So the cost is going down, but there need to be new technologies in sequencing in order to get the cost down to be relevant for DNA data storage. So again, this is not a technology that's available tomorrow. We're showing you things that like very early on in its roadmap, and it will take a few years to get the cost down of both the synthesis and sequencing in order to make it viable.
Will I be able to buy a USB DNA drive? Or is it just for enterprise use like tape libraries or something like this?
Yeah, that's a great question. The thing is that like, unlike other forms of media, you can easily make a copy that you can give the customer. So you might be able to hold a copy of your data. Not a USB drive in a sense that you can plug it easily into your computer. But right now, there are readers that are on a USB stick that you're able to read DNA. Just the process is not something you do at home with the chemicals and stuff, but it might be. But again, the main applications that we see is more in the data center, behind the scenes.
Okay.
And even more so in very cold archival, right? I mean, certainly the first generations of this, once and if it deploys commercially, will be archival applications.
Okay. Thank you.
Yeah. And this is just to give like how a random access can be done on DNA, because this is very important. As long as the cost of reading is high or takes a lot of time, you might want to kind of be able to take a small part of data in order so the cost will be low to read it. And these are two approaches that have been shown to work about like how we can take only parts of the archive in order to read it. And I won't get into the details. Also, I'm seeing that we don't have much time. But just so you'll know that it exists and it's a valid way in order to read small parts of the archive. Last slide. So as part of developing this is why we started the Alliance. We wanted to build a data storage ecosystem. We see it as very important to have it interoperable because some companies are building the writers, some companies are building the readers, some companies are doing the storage, and it's very important that they will talk to each other. Both to give customer confidence, that customer will know that if they have an archive from one company, they can read it with another company. They're not dependent on one company for the solution. And we started October 2020. It was Illumina, Microsoft, Twist, and Western Digital. A year and a half ago, we moved to be under SNIA, a technology affiliate, because we wanted to develop some specs and standards in this industry. You can see some of the leading storage companies are part of the Alliance. And we're really now about to release our first spec and standard, which talks about how to find the first sector of a DNA archive in order to boot it up, and kind of like a master boot record. This is it. Happy to answer a few more questions.
Yeah, maybe we've got a couple.
You have, but we're also don't have much time.
I did feel that you spent a lot on the storing and like 20 seconds on the reading. The reading, it's kind of the important part. I found that really. I didn't even fathom that that the way of reading it might be destructive. That just seems counter. Like, why even look at a way of reading it that's destructive?
No, that's like
what's that?
No, it's like an atomic clock when they first discovered it. They smashed things with the accelerator. So PCR technology will look for restriction enzymes and look for key sequences to cut and splice and sequence. So that's a destructive methodology. But using DNA in this method, when they go through the whole thing and scan it all and then read each part, is non-destructive. So they haven't explored RNA technology to dedupe and compress it and to figure out all those mechanisms.
Yeah, it's definitely an issue that we're trying to tackle. But again, the ability to copy the DNA in almost free cost is that whenever you want to read it, and again, this is used for very cold data, like data that you probably won't ever access, or
Right.
you will need to access once in, I don't know, 10 or 20 years in case of a disaster. It kind of gives you an insurance for your data. This is the ultimate insurance, to put it over
Right.
there. It's not about replacing tape. Like, this is a complementary technology to tape. Tape, you'll need to have an active archive to access when you need a fast bandwidth. You need to read it fast, like compared to DNA, not as fast as hard drive and SSD. But yeah, the idea, and when you need to do it, you can easily make a copy, destroy the first one by reading it, and then you have another copy to save for the next time that you will need to read
Since
it.
the copies are so small.
Oh,
it's
so you
just not-
copy, then read. The copying doesn't destroy.
Yeah.
It's
Copying
direct-
doesn't
correct.
read. Yeah, of
Yeah.
You
course.
copy, then you
Yeah,
go
yeah.
and read. Okay.
Yeah,
All right.
and the copying is almost free. So the first synthesis is expensive, the
Mhm.
first one that you do it, but then to make the other copies with PCR, you give like sugar and chemicals to an enzyme, and this enzyme makes like tons of copies, as much as you want.
Yeah,
So it's pretty impressive to
great.
make a lot of copies. And
It's configured in a double helix kind of configuration. I mean, the data is
after PCR, yeah.
Yeah.
After the PCR. So what the stable form is DNA, or stable form is RNA?
It's DNA. It's not RNA. And this is not a biological kind of DNA that is run by enzymes that convert it to RNA. It is like synthetic DNA that is not interacting with any enzyme or something like that. So it's not like live DNA in the chip or in this tube that you have.
Archive will not become a Frankenstein monster if I inject it into a mouse.
No, it won't happen.
not yet.
Okay.
At least the possibilities are low.
Quick question on that point. So you're saying that you copy the data before you then read it because the structured part there. Yeah, that right?
Yeah.
Because then what does that kind of error checking process look like when you make these copies to make sure that it is identical? I noticed earlier in the slides you had a mention of the error checking and stuff, but yeah, that's the part that to me then thinks, okay, well, how do we know if we're effectively doing a copy before a read and that? I'm just thinking of, data mutated effectively is the only kind of term I can think of for it. But yeah, quite curious as to any challenges you guys have been having with that and what you're seeing really.
Yeah, so the PCR process is a very, very accurate and very proven method of copying. It has a very, very low error rate. And this is, of course, why we also employ the ECC and the error correction and detection codes inside the DNA. So we are not that worried if some copies will get some errors in the process of copying, as each packet has like so many copies inside that if in some of them we have few errors, like this can be easily fixed both in the sequencing process and in the decoding process after when we're using the codec. So far it's been shown to work really, really well. And again, this is not meant to be read every hour, every day or something like that. This is more like to be read when you have a disaster recovery thing or every few years or you can't reach it. It's kind of like you set this data and forget about it, and you don't need to worry about the technology being obsolete, the data being rotten or anything like that. Like you put it and you have this insurance of your data on the side.
And I know you said not ready today. Is this 10 years out, 5 years out?
It's a great question.
Depends
We
who
can
you
buy
ask.
something.
Yeah, it depends who you ask. And
5 to 10?
yeah.
It's a ways out.
Yeah, so we proven that the whole workflow works. Like we're currently seeing projects that are done on the megabyte scale and soon on the gigabyte scale. And it's going to get to the terabyte scale. So it's a matter of like scaling up. It's not a matter of that. We don't have building blocks that haven't been proven or not working and are kind of like in an R&D challenge. Like the full process works. It's now about scaling it up. It's kind of like when we were in the early days of the USB sticks, USB drive that was only like 8 megabytes or 16 megabytes. And like you need to scale it up in order to get to...
the fundamentals are there, and the scaling is what the tech industry has a good track record of doing. So that's the phase that we're in. Nonetheless, it's going to be years.
You've done the important step because you've printed the T-shirts.
Yes. Yes. Great way to end up. So we should get off so Sham can get...
Do you guys have a final word that you want to leave the audience with or anything?
I mean, if you guys are interested, you're able to follow us both on LinkedIn and Twitter. We post updates about this technology, about what's happening in order to keep the world updated about this. It's a really exciting technology, and it's really like a key thing in order to solve a lot of the sustainability issues with the growing like data centers and the power consumption and even the real estate that data centers are taking. So it's a great way to follow it, and hopefully you'll see it soon in your data center.